Yesterday we looked at measures of central tendency. We looked at mean, median, mode. Well, another factor that we like to look at for a data set is how variable is the data. Not just where is it centered, but how spread out are the numbers. And one real kind of archaic way of doing that is to look at the range, which we know the range is the difference between the high and the low. But that only takes the upper number and the lower number into account. So we also have the inner quartile range as a measure of spread, and we know that we calculate that by taking the third quartile minus the first quartile, and that tells us how the range of the middle 50%. But we have two other types of a little more sophisticated ways of measuring how spread out the data is, which uses all of the values. And those two concepts are called variance and standard deviation. So here's the variance and here's the standard deviation. And they're very much related. We have some formulas here, and what we're going to do is just go right to an example, and then we'll go back and look at the formula. It will make more sense if we look at the calculation and then look back at the how it fits with what we'll have up above. All right, so first of all, we have to determine, in order to find the variance and standard deviation, we have to determine the mean. So we have to add up all the numbers and divide by how many there are. And I already did that. I added up these values, of which there are only 5, and I got my mean to be 91. So that's the measure of center. We do not use median or mode when we're calculating a standard deviation or a variance. Now, the next thing we have to do is we're going to find the variance first. You will actually always find the variance first. And the symbol for us for a sample is going to be an S squared. So we're finding a sample standard deviation. This is just a sample of numbers. And the variance symbol, again, is S squared when we have a sample. And what we need to do is we need to subtract and find out how far is each of these numbers from the mean. So we're going to, let me just take a peek up here. We're going to take each of our numbers, which we're going to call an x, and subtract the mean from it, and we're going to square it. And this difference is called a deviation. So we're finding how far each of the numbers is from the mean separately and squaring each of the deviations. So we're going to need each deviation squared. That's the first thing we're going to do. So I took each of these numbers and I subtracted 78.2 minus 91, and I got negative 12.8, and I need to square it. Now I actually don't need to put the negative down since I'm going to be doing the squaring. I'm going to write them this time. Typically I won't put it down because I know I'm going to be squaring them and the negative is going to cancel out. I need to take the 90.5 minus 91, and that's negative 0.5, which again I don't really need to put the negative down because I'm going to be squaring. I take the 98.1 minus the 91, and that gives me 7.1, and I'll be squaring it. The next deviation, 93.7 minus 91. So I have 2.7 squared. And then my last, 94.5 minus 91, that difference is 3.5, and I square it. So my first step in variance is to find how far is each number from the mean squared. Then I add those all up, and I divide by, when it's a sample, 1 less than how many numbers I have. And that calculation will give me what is called the variance. So let me write that down. When I did that calculation, I got 58.51. That is my variance. Now let's go back and look up at the formula. The formula tells us to find it, we have to find how far each number is from the mean squared. Sigma means we will be adding up all those numbers and then dividing by 1 less than we have. And this is for a sample of data where we don't have the entire population. On the other hand, if we had the entire population, a different symbol is used. This is called a sigma. Now, this notation here is also called sigma. That's a capital sigma, that's a lowercase sigma. And this sigma squared is showing me that this is the population variance. And if we had every single number in the data set, then we would be finding a population variance. almost always, and for our class it will be always doing this, we have a sample, we will always be finding an squared as opposed to a sigma squared. But the formula basically looks the same with one little exception. The only difference is the symbol, if we have a population mean, is this symbol, looks like that, and that's called mu, and that's a population mean, as opposed to this x bar is a sample mean. Okay, but for us, we're always going to be calculating this. If you had every single number, we would add up all the deviations squared, and the only exception that's different from here is we divide by n as opposed to n minus 1. And in AP Stats we talk about this more, but again, we will be working with sample data. We would love to have all the data and be able to calculate this like this, but it is highly unlikely that that's going to happen. And what we're really finding when we find variance is we're finding the mean or the average of all the squared deviations from the mean. So we're finding what the squared deviation is from the mean and finding the average of the squared deviations. So we're finding all the squared deviations and dividing by adding them up and dividing by n. So we're really finding the average squared deviation. Now, standard deviation, the only thing that's going to be different is, let's quick peek at this formula. The standard deviation is all I have to do is take my variance answer and square root it. That's going to be easy. So my standard deviation, S, is just going to be the square root of 58.51, and that gives me 7.65. That is my standard deviation. Now, technically, the standard deviation is the square root of the mean of the squared deviations. The standard deviation is a way of detecting how variable the data is or how spread out the data is. So the measure, it's a measure of how far each value varies or deviates from the mean. It will be approximately equal to the average the values are from the mean. Another thing that's nice to know is that this standard deviation is pretty close to a fourth of the range. It's not going to equal it dead on, but it will give you kind of a judgment as to whether your number seems to be really far off. Okay, so let's look at next page. Now, another thing that we like to do is we like to be able to compare values. And one way to compare is to look at a distribution or compare two numbers. This is to look at its z-score. And the z-score is going to be calculated by taking a score minus a mean. It's technically supposed to be a population mean divided by a standard deviation, but we will also use it, take a score, and subtract away the mean, because most of the time we will have sample data, and divide it by the standard deviation of the values. So we'll take a value minus the mean of the data and divide it by the standard deviation. And again, it's best if we have a population standard deviation, just a lot of times we have samples. And what does this do? It measures the number of standard deviations, the value is above or below the mean. So what it does is it takes and, relatively speaking, tells how far you are away from the mean. So if you have a z-score of 0, that means you are exactly at the mean. If you have a z-score of 1, that means you score 1 standard deviation higher than the mean. So let's go down and look at an example of values, and then we'll come back and have you practice. Now, I have the number of points that Darden scored in each of 11 basketball games is listed below. So his lowest points was 5, highest was 13, and it says, within how many standard deviations of the mean do all the values fall? All right, well, first of all, I need to find what the mean is. And so I added all these numbers up and divided by how many there were, and I got 9.64, or approximately 9.6 points. Now I need to find the standard deviation. Now my standard deviation, I know I will be doing one big square root. And I need to find how far this number is from that mean, and that first difference is negative. 8 minus 9.6 is negative 9.6, but I'm not going to worry about the negative. I'm just going to call it 1.6 squared because I know I'm going to be squaring it. This next difference, if I take 12 minus 9.6, that gives me 2.4, and I know I'll have to square it, and so on. And I'm going to go to the last one. The last one, 8 minus 9.6. Again, that's negative 1.6, but I'm just going to write it as 1.6 squared. And I know I need to add up all of those squared deviations and then divide by one less than how many numbers I have. Now, I know I have 11 numbers, so I know I'll be dividing by 10. And remember, all that fraction has to be taken care of. And when I do this calculation underneath the radical, I'm actually finding the variance. I'm finding the mean of the squared deviations. And then when I square root it, I get the standard deviation. And I calculated that to be 2.54. Okay, so that tells me that about on the average, if I know the mean is 9.6, about on the average, the deviation of his game scoring is about 2.5 points away from this mean. Now we're going to find the z-score of the low value. And the z-score, remember, is we will take z of the low. We will take the score, that's the low, and the lowest was 5. And we take the mean away from it. And we divide by the standard deviation. And when I calculate that, I get negative 1.8. And that tells me that his low is 1.8 standard deviations below the mean. His high score, on the other hand, I take his high, and his best game was 13 points. Take the score minus the mean, divided by the standard deviation. And when I do that calculation, I get that to be 1.3. So that means that his high he was 1.3 standard deviations above the mean. And so if I answer the question, it said within how many standard deviations of the mean do all the values fall? Well, here's the mean, which would be a 0. His low score was down here at negative 1.8 standard deviations away from the mean. His upper score was at 1.3. And so all of his scores, and we could find all the other z-scores for his other games, like when he scored 12 points and 8 points, etc. But all of them they all lie within 1.8 standard deviations. Okay, they all lie within 1.8. Now, it says, using the data above, within how many standard deviations would a score of 7 fall? If we want to find that, we want the z-score. We take the 7, we subtract the mean away from it, and we divide by a standard deviation. And we find out with that calculation that we get negative 1.02. So basically, 7 falls within 1 standard deviation of the mean. And then I have a set of values with a mean of 22 and a standard deviation of 5. Find the z-score for that value. Explain the meaning of the z-score. Again, we know the mean and the standard deviation. So it's z-score, and we want to find what a value of 30 is. 30 minus the mean divided by the standard deviation. And that means that a score of 30, the middle value or the average is 22. Standard deviation, or that's the measure of how spread out the numbers is for this situation, and we know that if a score has a z-score of 1.6, that the score of 30 is 1.6 standard deviations, because it's positive, above the mean. Now, here's the last one. A set of data or a set of values has a mean of 85 and a standard deviation of 6. Let me make a little number line. So here's our score of 85. It would have a z-score of 0. If we have a standard deviation of 6, if I add on 6 values to this, I'd be up at 91. That score would have a z-score of 1. If I add on 6 again and go up to 97, that would have a z-score of 2. If I go down 6 units, down to 79, that would have a z-score of -1. This score would be 1 standard deviation of 79 would be 1 standard deviation below the mean. 97 would be 2 standard deviations above the mean. Okay, so that's the context. And quite often, I'll talk about this more when we're in the normal distribution idea, you don't very frequently have numbers that are more than 3 standard deviations away from the mean. It's very unlikely to have a data set that has numbers who are higher than 3 standard deviations away in each direction. So let's go back to this question. We have a set of data has a mean of 85 and a standard deviation of 6. So it looks like this. And we want to find the value that has a z-score of 2.5. Well, we know 97 has a z-score of 2. And so we could figure out what a z-score of 3 is. And then we could actually just kind of analyze this and figure out what the value is. So we know it's bigger than 97. But it's real slick if we just use this idea. And I'll use the sample mean here. We want the z-score to be 2.5. We don't know what that number is that's at that spot. We do know the mean is 85 for the data set, and we know the standard deviation is 6. We have a little equation. All we have to do is solve it. If we multiply both sides by 6, we end up getting 15 is equal to x minus 85. Add 85 to both sides, and I get 100. So if we analyze this situation, this 100 value, or go 3 units up, would be right at the spot, which would be 2.5 standard deviations above. We use z-scores constantly in statistics, so this is a very, very important concept, just the beginning of it, and you'll be using it a lot more in the next unit as well. So now you're ready to practice.